Traffic barriers are key elements in our effort to design and build the safest highways possible. Like most other highway safety devices, traffic barriers are usually of only passing interest to motorists. That is, they're of passing interest until someone hits one. Then they become objects of primary interest, life and death interest. How well they work determines whether or not the motorist is seriously injured or killed. Construction, maintenance, and repair crew people need to know how to correctly install, maintain, and repair these systems so that they can work as well as they were designed. This series of 5 programs outlines the general procedures that must be followed with the most commonly used roadside barriers, median barriers, bridge rails, and end treatments. Each program of the module describes how the various highway features work, why they're used, and what factors to look for that might cause them to fail. The programs also give examples of how the different systems are initially installed, then maintained and repaired. The first of the 5 programs discusses the cable barrier system. Program 2 of the series concentrates on the box beam weak post system. Program 3 covers strong post systems, the W-beam rail on steel or wood posts. Program 4 discusses the installation, maintenance, and repair of the concrete barrier, both its standard section and the various end treatments used with the system. In the final program, the installation, maintenance, and repair of various kinds of end treatments are reviewed. The program highlights these different designs: the breakaway cable terminal, the flared and buried end, the twisted and turned down end, the sentry system, earth berms, and crash cushions used as end treatments in different situations. Before discussing these programs, let's review the general purpose and function of barrier systems. Webster's dictionary defines a barrier as an obstruction, anything that hinders or blocks. Basically, that's what we expect traffic barriers to do, to block or prevent a vehicle from running into a more hazardous object. In a government manual commonly known as the AASHTO Barrier Guide, definitions of the 3 basic types of traffic barriers are given. A roadside barrier offers protection from one side only and applies to roadside hazards. A median barrier gives protection from both sides and applies to the separation of opposing traffic. Bridge rail barriers provide protection from one side only and are used to keep the vehicle from going off the bridge. They may be used occasionally to protect pedestrians from vehicular traffic. Traffic barriers are classified according to their stiffness. They're identified as flexible, semi-flexible, or rigid systems. Traffic barriers have 3 parts, each designed to do a different job. These parts are the end section, the standard section, and the transition section. To function properly, these individual parts must work together as a complete system. Traffic barriers are carefully tested and evaluated before they're approved for use on the highways. But even though a barrier system has been accepted as a standard construction item, its performance will be affected by the way it's installed and maintained. And that's where you, your skills, and these 5 programs come in. The programs will review the factors that determine whether or not these barriers can work as they should. Have you ever wondered at the end of the day if the traffic barrier you installed was done properly? Well, this series of programs will provide the information you need to be sure that you've done a good job. Before viewing these programs, it's important that we review some of the basic factors that can affect traffic barriers. Traffic barrier selection, meaning the choosing of one particular system to meet a specific safety need at a certain location, depends on 4 things. 1, the type of hazard requiring a barrier. 2, the distance from the barriers to the hazard. 3, the distance from the barrier to the flow of traffic. And 4, the cost and required maintenance of the system. These factors can change quickly along the roadway, so the type of barrier selected generally fits the prevailing kinds of hazards and their locations, as well as the kinds of vehicles using the road. Obviously, the kind of hazard will largely determine the type of system selected to provide the necessary protection. For example, the barrier required for a rigid bridge pier would be different from one needed for a steep embankment. The barrier must be capable of retaining, decelerating, and redirecting a vehicle in such a way that no serious injury or death occurs to the passengers. When selecting and installing a barrier, it's very important that it be placed on relatively level ground. The cross slope of the area in front of the barrier should not be steeper than 10-to-1, and curbing must not be installed in front of the barrier. Either of these conditions could cause a vehicle to vault over the barrier instead of striking it at the proper height. If vaulting occurs, the system has failed. If the system fails, death or injury will likely follow. The distance from the barrier to the hazard is important. If the barrier deflects inward all the way to the hazard, it obviously will not provide much protection for the motorist. The distance from the barrier to the outside lane of traffic is also important. A barrier must not be installed so close to a traffic lane that an impacting vehicle could be redirected back into the traffic flow, or the barrier itself be deflected into the normal traffic lane. Finally, the required maintenance and the cost of the system need to be considered when selecting a traffic barrier. In general, flexible systems that are more forgiving when they're hit are best for the driver. But unlike the more rigid systems, flexible barriers receive more permanent damage with each impact and cannot sustain repeated hits without immediate repair. The trade-off is to use flexible systems where they can be set away from the roadway and not be hit so often. Semi-flexible and rigid barriers, which are less susceptible to damage, can be placed closer to the roadway. This strategy balances safety and maintenance costs. Now that you've completed this overview of traffic barriers, please continue with the remaining programs. They review the standard procedures for installing and repairing the steel cable, box beam, W-beam, and concrete barrier systems. When you finish the series, you'll know what each system is and is not expected to do. And you'll know what to look for when you install, maintain, or repair a barrier. Sometimes, when you're out on the road dodging traffic, it's easy to forget how important your job really is to those who travel the highways in your work area. Lives are literally in your hands. The wrong flare on an end treatment, posts that are spaced incorrectly, guardrail that's set too high or too low, bolts that are missing from a splice, a cable that isn't tight enough. All these little things can cause a traffic barrier system to fail. It's not stretching the point to say that you could personally save a life by paying attention to the details of your work. For the sake of all highway users, including your own family and loved ones, learn from these programs and apply what you learn in the field. The reward is beyond measure. As the technology of highway safety equipment increases in complexity, the people who install, maintain, and repair these systems must be kept informed of the new technology. This program will help you stay informed by providing the general knowledge that's needed to properly install, maintain, and repair the W-beam steel strong post system or the W-beam wood strong post system. More specific instructions concerning installation, maintenance, and repair of strong post systems should be provided through individual state standards. However, this program will help you understand why these systems were developed, how they work, and what can prevent them from working as they were designed. First, let's review the major functions of the two systems. W-beam strong post systems are semi-flexible traffic barriers that are designed to stop, slow, or redirect any vehicle that hits them. The barriers are made up of three basic parts: an end treatment, a standard section, and a transition section. All three components are required to make up a system. How these parts are individually designed will depend on the terrain and location of the hazard. The end treatment does two major things. First, it anchors the entire system at each end of the barrier. Secondly, it protects any impacting vehicle from the more rigid sections of the barrier. End treatments come in a variety of shapes and sizes depending on the requirements of the system. They may be built to fall down on impact or to absorb the full force of a head-on hit by pocketing and retaining the car. To a lesser degree, this is also true of the standard and transition sections of these systems. The standard section of a strong post system is usually not hit head-on. It's normally hit at an angle and must be strong enough to deflect the vehicle and redirect it away from hazardous conditions. The effectiveness of the standard sections in a barrier system is influenced by the system's length, how the standard section is attached to the rest of the system, the height of the barrier, the roughness and slope of the terrain, and the rail tensile strength. The purpose of the transition section for most strong post systems is to provide a smooth, continuous change from one type of barrier system to another. This section may also function as either the upstream or downstream anchor of the system to a bridge. The transition section is designed to gradually increase in stiffness as it goes from the flexible guardrail to the rigid bridge rail. It is stiffest at the bridge end to allow less deflection at this critical point in the system. The stiffness prevents the impacting vehicle from forming a pocket in the guardrail and hitting the bridge end. The transition forms a smooth flare in the rail from the flexible section to the rigid section. It's necessary to maintain a level barrier height through transition areas to ensure a smooth progression or change from one barrier to another. Now let's get into a general review of installation, maintenance, and repair procedures. The W-beam steel strong post system uses a 6-foot-long steel wide flange beam as the post that supports a rail of 12-gauge corrugated steel. The rail is blocked out from the post. The standard rail length is 13.5 feet with splice connections overlapping every 12.5 feet. One of the most important safety features of this system is found at the splice connection. All 8 bolts must be used to provide enough strength at the splice joint. Fewer bolts will produce weak splices that can easily separate when the rail is hit by a car traveling at normal highway speed. A single 5/8-inch diameter buttonhead bolt located in the center valley of the W-beam is used to connect the rail to the block and the posts. Some states use a rectangular flat plate washer with the buttonhead bolt to prevent it from pulling through the face of the rail. However, washers should not be used in the standard sections of the strong post systems. The offset block or block out sets the rail 6 inches out from the face of the post. Many early guardrail designs were not blocked out, and this caused some problems. When a vehicle hits a rail that is not blocked out, the impact will often flatten the rail. Instead of sliding along the face of the rail, the vehicle will penetrate beneath it, snag a wheel on a post, and spin out onto the roadway. The addition of the block out will help prevent this problem in most situations. A 12-inch long section of 12-gauge W-beam rail is placed behind the rail at each post where a splice does not occur. This piece of W-beam acts as a backup plate and prevents the rail from being cut on the edge of the post. If the rail should be cut this way, large segments of the barrier system would lose tensile strength and fail to function properly. The separated ends of the rail could even spear the impacting vehicle. Backup plates are not needed at splice connections because the overlapping rail provides a double thickness. In the W-beam wood strong post system, the same type of rail, a 12-gauge W-beam, is carried on wooden posts and is blocked out. While similar to the steel strong post system, there are important differences. First of all, the rail is connected by a single 18-inch bolt that passes through the blockout and the post. This bolt is much longer than the one used in the steel post system. Distances from the top of the blockout to the top of the post may vary from state to state. Previously, a flat plate washer was used on the face of the rail. However, experience has shown that this washer is not needed. A round washer is used under the nut that fastens the bolt to the back of the post. Since there's no tendency for the rail to be cut on a wood blockout, no backup plates are required. 1 or 2 nails toe-nailed through the blockout into the post will keep the block from swiveling on the single bolt connection. Sometimes a hole is drilled through the blockout to prevent it from splitting later on. Keeping the blockout in place is obviously important. It has to be lined up with the post to properly support the guardrail. Although mounting height standards vary from state to state, most use standard 6-foot steel or wood posts and mount the guardrail at a height from 27 to 30 inches. This height allows 3 feet of soil support for the post. Now that we've reviewed basic installation, let's check some things you should look for when doing routine maintenance. When inspecting end treatments, examine existing hardware like bolts, washers, and clips for signs of damage. The key to the effectiveness of the end treatment is its anchor to the footing in the ground. All cables must be properly attached and tensioned. These inspection points are critical. The standard section makes up the longest part of the barrier and should be inspected as closely as the other sections, since it is the part of the guardrail that absorbs most of the impacts. Here are some questions to ask when you check it out. Are the posts properly embedded? Is there enough soil behind the post to prevent them from being pushed out on impact? Is the height of the barrier correct? Is it consistent through the system? A range from 24 to 30 inches to the top of the rail is a common requirement. Is the rail face smooth? Are splices lapped in the direction of traffic flow? Are post connections properly installed and tight? And finally, do the rails, support posts, or other elements show any signs of corrosion or damage? If so, have you taken corrective actions? Transition sections of W-beam strong post systems are usually easy to inspect. Make sure that all connections are correctly installed. Transition section bolts tend to loosen where guardrail and bridge railings join. Make certain they're tight. Check to see that the section is properly stiffened. Is the flare rate smooth and without projections that could snag a vehicle? Is the beam installed properly? Are the required extra posts correctly installed? Where weakness is present, a section of tri-beam rail may be needed to make the rail stiffer. Like the other barrier sections, see that the transition section is free from curbs, abutment ends, or other obstacles that might vault, snag, or tumble a vehicle. The height of the transition section barrier is very important. It must be correctly positioned at each end to match the height of the barrier it will connect to. The different systems around the country may vary, however, basic repairs are the same. The following repair crew demonstrates their technique on this W-beam strong post system that's done its job, and it's now up to them to put it back in service. Upon arrival at the worksite, the first order of business is to set up a traffic control safety zone. The crew begins the repair work by first loosening the connecting nuts and bolts of the damaged system. After the nuts are taken off, the damaged guardrail can be removed. Care must be used at this point. Kinked or bent guardrail must be cautiously removed. Railing that is distorted with bows or kinks can build up a lot of internal tension. When the railing is pulled free, it can spring back and injure someone. When all of the guardrail has been taken from the posts, it's set aside until cleanup. Whatever can be salvaged is set aside for later use with the system, but bent pieces aren't used until they've been straightened. When the worksite is cleared of damaged rail, the damaged posts are removed. Wood posts may have to be dug out or pulled out with a chain and hoist. Steel posts that have been slightly twisted can often be straightened in the ground. At this point, the post hole needs to be cleaned up and adjusted to proper depth. Next, place the posts and attach the blockout and, if needed, backup plates. A tape measure or string line is used to adjust the post to their proper position. The crew next begins hanging the guardrail. It's more convenient to start the new guardrail from the downstream end of the system, since the rail is to overlap in the direction of the flow of traffic. A drift pin can be used to line up the holes in the guardrail and posts as the rail is being hung. Nuts and bolts should only be finger tightened at this point. Backfill and tamp the soil around the base of the post until they're firmly embedded in the ground. If the posts are near a slope, there must be a minimum of 2 feet between the post hole and the top of the slope. When all the W-beam has been hung, all the nuts and bolts should be firmly tightened. And where needed, toenail the wood post. Finally, when all the repair steps have been completed, the work area should be cleaned up and the elements of your safety zone removed. Remember, in all repair or installation work, be sure to follow your state's guidelines. The W-beam wood and steel strong post systems, widely used as a protector for our nation's highway users. Traffic barrier safety systems, whether they be roadside barriers, median barriers, or bridge rails, all need an end treatment. It makes no difference what type of barrier is involved. It can be flexible, semi-flexible, or rigid. All must have some form of end treatment. In this program, we'll look in some depth at 4 end treatments: the breakaway cable terminal, the flared and buried, the twisted and turned down, and the sentry end treatments. Barrier systems are built to slow, stop, or redirect cars that hit them. This requires the design and construction of a barrier system that acts as a single unit when called on to do so. All parts of the system, the end treatment, standard section, and transition section, are important in supplying this required action. However, end treatments are probably more important than the other 2 parts. Why? Mainly because they anchor the upstream end of the system and, when designed to do so, the downstream end too. But also because if they fail to carry out their function, then the entire barrier system could fail. And if the system fails, passengers in the car involved in the impact would probably be either seriously injured or killed. So as you can see, particular emphasis must be placed on the proper installation, maintenance, and repair of these vital parts of the traffic barrier systems in use throughout the United States today. Before we review the 4 end treatments that are the subject of this program, let us quickly examine the factors that influence the selection of almost all traffic barrier systems. When designers survey a location where it's felt a traffic barrier should be installed, they make their recommendations for the type of system to be used based on 6 major considerations. These are the type of hazard the motorist needs to be shielded from, the available distance between the barrier and the hazard, how the barrier will have to be located in relation to the traffic it'll be designed to protect, the maintenance that will be required to ensure the system is kept working correctly, the estimated cost of installing and maintaining the system, and finally, the type of systems in use in the highway agency in question. Now to the systems. The breakaway cable terminal end treatment is designed to work with W-beam barrier systems, but can be transitioned to work with the Thri-beam through the use of a commercially available transition piece. The Roadside Barrier Breakaway Cable Terminal, or BCT, is designed to break away at the first two posts and allow the vehicle to accordion the W-beam and pass safely behind it. To allow for this momentum-slowing action requires a finely tuned BCT system, the first post of which will shear off at a pre-planned point where a hole has been drilled in the wood post system, or where a slip plate has been installed if the system is supported on steel posts. After being hit downstream from the terminal, rail strength of the system is maintained by tension in the cable. There are 7 key elements that will normally determine whether or not the BCT will function as designed when impacted. These elements are post dimensions and the actual spacing of the posts, cable size, attachment, and tensioning. The breakaway system, either the hole in the wood post or the slip base on the steel post, footings of the first 2 posts of the system, the 4-foot parabolic flare in the last 37.5 feet of the rail, a critical element, the hardware used to connect the system, and available recovery space behind the end treatment itself. Post size and spacing are obviously very important. If posts are too small, they won't provide the designed-in resistance when hit. If they're too large, they'll resist too much. Approved wood post size for the BCT is 6 by 8 inches. Normally a Douglas fir post is used. Steel post measurements are 6 by 8.5 inches. Posts are set on 6-foot 3-inch centers. The first 2 are not blocked out to prevent fouling on impact. Although no more than the first 37.5 feet of rail functions as part of the system, the flare must be maintained beyond this point if so designed. The first post of both the wood and steel post BCT systems should be drilled with a 2 3/8 inch hole. On wood post systems, the cable, attached by 8 bolts to the back of the W-beam section ahead of the second post, passes through the first post and attaches with a plate to the front of that first post. A steel insert is used through the drilled hole to keep the cable from tearing the wood post. The cable must be kept tight. 3/4 of an inch of deflection is acceptable. For steel posts, the cable passes through the first post above the slip base. The plate extends down to the bottom of the lower stub plate so that the slip base is not activated by cable tensioning when it's impacted downstream from the end. When the system is impacted on the end, the wood post breaks away. In the steel post system, it slips away. And this action releases the tension in the cable, allowing the W-beam to buckle. Depending on the size, weight, and speed of the impacting car, beams in the end treatment continue to buckle until the vehicle is stopped. A bulb on the front of the system is intended to distribute a head-on collision's weight and force. It flattens out, preventing the W-beam rail from spearing the impacting vehicle. Here's a new bulb just prior to installation, and one that's been hit and done its job. To make sure this bulb functions properly, care must be taken to see that the wraparound connection on the back of the W-beam is tight and that all bolts have the right-sized washers. Otherwise, the bulb could tear loose on impact and the W-beam could spear the vehicle. To ensure that the first and second posts of the system break away and are not pushed over when impacted, they're set in concrete footings of at least 3-foot depth. The surrounding soil must be stable. A loose sand will not work. Removal of broken stubs has created some problems, with several solutions being worked out. A styrofoam sleeve and a steel sleeve with soil plates are 2 different concepts available. Another solution has been to place a heavy pressed paper tube around the post when it's installed. The footing is poured around the outside of the tube. Now, care must be taken to ensure that no concrete is placed between the tube and the post. Once installed, the paper tube absorbs water from precipitation and is softened so that the post stub pulls out easily. Much of the tube comes out with the stub. The remainder can easily be removed from the hole since it does not adhere to the concrete footing. Stub posts can quickly and easily be removed from this type of footing, which meets installation specifications. Flare characteristics of the BCT are critical to its proper performance, particularly with the smaller vehicles that might impact the system. Head-on hits with unflared roadside barriers can cause severe damage to these smaller cars. Flare for the BCT must be parabolic with a 4-foot offset from the tangent section of the railing. Length of the BCT is also a critical factor in its reducing injuries and deaths when hit. Recommended length is 37.5 feet. Some agencies have extended the terminal length to 50 feet, anticipating the extra length will offer more energy absorption capacity. However, since the BCT is intended to divert an impacting vehicle to one side of the barrier rather than absorbing its kinetic energy, the extra length provides no added capability. Connection hardware for the BCT system simply cannot be changed from what is required by specifications. If even minor changes in bolt size or strength are made, the system will normally fail to function as designed. 8 bolts must be used to connect the cable block to the rail. Cable anchorage at the first post must be accompanied by a 3/8-inch plate. Beam splices must be lapped in the downstream direction to avoid snagging an impacting car. All bolts must be the proper size and must be tight. After the first 2 posts, blockouts should be used. No washers should be used on the first 8 posts of the W-beam post connection bolts. This allows the railing to tear loose from the post and to bend outward more easily on frontal impact. Leaving off the washers on all post bolts is acceptable practice. Check your specifications for guidance in this matter. Finally, recovery space is a major consideration when a BCT end treatment is used. Obstructions like the utility pole shown here cannot be located within the treatment. The whole idea of the BCT is that it bend backward when impacted near or at the nose. Common sense then dictates that there be an area behind the treatment that will allow the impacting vehicle to regain some degree of control. This is not possible if there's no recovery room available behind the system. The driver would simply be trading the frying pan for the fire. So the area behind the BCT should be free from any fixed hazards and as flat as possible so that no secondary impacts will occur. No signs or other roadside obstacles should be placed within 200 feet of the BCT. Terrain leading to the barrier needs to be as flat as possible so that any impacting vehicle hits it at the proper height. The flared and buried end treatment is often used when the fear of spearing is a concern. How does it accomplish this task? The end of the treatment is simply buried and anchored in a cut section. However, there are still some considerations that must be dealt with in this end treatment procedure. First, the flare must be correct. And in using the design, particular care must be given to maintaining proper barrier height. This might present some difficulties, particularly if the treatment must cross ditch lines. Also, if a cut slope is being used for burying the end, long sections of railing may be required if the cut slope is located some distance from the roadway. The barrier height problem simply means that if the top of the rail is too low, the impacting vehicle may vault it. And if it's too high, the vehicle may go under the barrier. Both of these possibilities must be avoided. Anchoring of the system is normally accomplished by the upstream end being bolted to a concrete footing in the cut. 8 bolts are normally used, providing positive connection to develop the full tensile strength of the rail. Then the slope is restored to its normal shape. Various designs of the twisted, turned down Texas twist and anchored end treatment have been used in several states. For our purposes, we'll call this end treatment the twisted and turned down treatment. The major problem with developing this system has been with cars vaulting and or rolling over. This occurs if the impacting vehicle rides up on the twisted section of the system and crosses the first backup post. Modifications to the system have now made it a workable one. Basically, what has been done to correct the problem involves removal of a post and rigging the railing so that it can fall down when impacted. This is called CRT, or Controlled Release Terminal. One variation is the clip and short section of W-beam. Other variations perform in the same manner. Fundamental to the system's working as designed is the requirement that the rail release from the supporting posts as soon as the end treatment is loaded with a downward force. Various rail post connections are used. To set up the system, a short section of W-beam is bolted to the posts. The barrier railing is then placed into this section and rigged to be held there by a weak galvanized steel clip over the top rib of the rail. Any significant downward load on the railing, such as the weight of a car, pushes the rail down from this connector and allows the W-beam to fall harmlessly to the ground. The impacting vehicle then either continues on to shear off weakened posts or until it decelerates to a stop in a runout area behind the rail end treatment. With this system, spacing of the first 3 posts is important. The twist and turn down occurs in the end 25-foot section. No post should be set within the twisted section. The second and third posts are spaced 12.5 feet apart, with remaining posts set at 6-foot 3-inch intervals. After passing down the first section of rail, the 25-foot section, the vehicle will either shear off or knock over the first 3 posts, depending on whether they're wood or steel, and slowly decelerate to a stop. The twisted and turned down end treatment should be flared out at least 2 feet, preferably 4 feet, to be operationally functional. The turned down end of the system should be anchored by 4 bolts to a concrete footing that's either at or below grade level. As mentioned earlier, the rail is intended to release from the first post and lie down. To bring the required quick release, several systems have been developed that work like these galvanized steel clips. A recent addition to the guardrail end treatment is the commercially available Sentry guardrail end treatment. This system combines features of other end treatments along with those of some crash cushion units. It has support posts with slip bases, collapsible Thri-beam fender panels, containers of sand on the first 3 posts, a cable terminal that assists in the slowing of the impacting vehicle while at the same time redirecting it, and a soft nose that collapses on impact, doing away with spearing dangers. When impacted in a head-on crash, the system's fender panels telescope in, the support post shear, and the cable of the system activates to redirect the car into its normal travel lane or slows and stops it. The sand containers on the first 3 posts of the system assist in the deceleration of the vehicle. Installation of the Sentry is relatively simple, as the manufacturer's installation instructions are complete and well illustrated. When combined with a standard work order and work plan, sufficient information on system installation is available to make putting the system into service an easy task. The tools and equipment required for Sentry installation are listed in the instruction manual. In anticipation of this installation, a level platform must be poured with a square anchor installed in the front and a rear anchor off to the side with its own concrete base as specified. The Sentry unit may be installed either on straight guardrail or on guardrail that's been flared away from traffic. 2 types of slip bases are supplied for the unit. The slip bases for posts 1 and 2 have flared slots, while the slip bases for posts 3, 4, and 5 have straight slots. Arrange the bases next to the proper post locations with ramp ends touching the ground before proceeding to the anchoring process. 4 basic anchoring alternatives are suggested by the manufacturer for the system. The first option involves driving a wooden post with a platform attached to the top of the post. The second option uses steel I-beam driven into the ground to anchor the unit. The third option calls for embedding L-bolts attached to the slip bases in 4,000 psi concrete footings. The final alternative uses expansion-type or flush-type anchor bolts to fasten the Sentry to a 4,000 psi minimum concrete pad. The manufacturer supplies additional anchoring information with the system. It should be reviewed along with your own state standards for anchoring procedures recommended for your area of the country. For purposes of demonstration, the concrete pad method will be shown in this program and how this particular crew performs their installation. Assemble post 1 in place first. Mount the base to the concrete by drilling the hole and then tightening down the bolts. Next, place 4 hex head bolts head down in the base slots with a flat washer on each bolt. Then place the keeper plate onto each slip base, followed by one flat washer on each base plate bolt. Position the post base over the bolts, followed by a flat washer and nut. Torque the nuts to 75 foot-pounds, plus or minus 5 foot-pounds. Careful alignment of the slip bases is extremely important. They must be aligned to each other as well as to the finished grade of the road. Check alignment parallel to the roadway once all 5 bases are in place. Posts 1 and 2 are similar, except for the cable hole in post 1. Posts 3, 4, and 5 are different from posts 1 and 2 and must be positioned accordingly. Next, attach a blockout with the 2 hex head bolts and nuts called for and tighten firmly. Once all posts and bases are mounted, then it's time for the mounting of the fender panels. Bolt a fender panel to post 5 using 2 hex head bolts, a flat washer, and a nut. Be sure to use the holes marked with the letter S. This fender panel will overlap the transition panel or thri-beam guardrail end. A 3/4 inch diameter hole should have been drilled in the transition panel end or the thri-beam guardrail end. If not already done, this hole should be drilled approximately 1 inch from the end of the slot in the fender panel. Place the mushroom bolt assembly through the fender panel and transition panel and secure it with a square washer and nut. Then tighten the mushroom washer nut to 60 foot-pounds. Remember, use holes marked S. Attach the remaining panels, starting with post 4. First, attach the panel to the post with 2 bolts. Then attach this panel to the previous panel using the mushroom bolt assembly. Continue the process for the remaining posts and panels. At post 1, the 3/4 inch bolt assemblies must be left loose. The plastic bull nose is positioned over the panel but under the flat washer and bolt head before tightening the bolt assemblies. 2 bolts are also placed through the 2 remaining holes in the bull nose and through the 2 fender panel holes labeled G. The cable is now ready to be connected. Place the front threaded end through the first post and on through the anchor. Install 1 square washer and nut on it. The rear anchor threaded end must go through the rear anchor, using as many square washers as necessary to install the nut without bottoming out on the threaded section. Tighten the cable by holding the swagged end with a pipe wrench and torque the nut with a torque wrench to 100 foot-pounds. The nut threads need to be fully engaged to the threaded cable ends. Next comes sandbox placement. The sand containers are attached to posts 1, 2, and 3 and are labeled with their proper post numbers. Place the correct container on each side of these first 3 posts. Use 2 bolts, 4 washers, and 2 nuts to attach the containers, sandwiching the post and blockout between the containers. Fill the containers with clean, dry sand to the top edges and snap the lids closed. After completing the installation of the redirecting cable, check to ensure that all fasteners are fully tightened throughout the unit, on the fender panels and other system parts. For future maintenance and repair of the system, the manufacturer of the Sentry unit provides well-designed procedures. At times, there simply will not be an appropriate end treatment available to meet a traffic safety need. That's when a combination of both a barrier system and a crash cushion system might do the trick. Crushable crash cushions can be used with some special needs, but the most common use of combining crash cushions with end treatments will be when they're used with rigid systems, such as the concrete traffic barrier. A final word, this concerning the installation, maintenance, and repair of these systems. Don't ever feel that you must memorize how all of these systems must be serviced. That's absolutely not required. What you do need to know is where to find the specifications that will apply to the system you're working on, along with a basic knowledge of how the various systems work. A checklist is particularly helpful in doing your job in a systematic manner. If you follow both your local standards and any available manufacturer specifications for the installation, maintenance, and repair of these end treatments, you'll be able to walk away from the job knowing that you've done your absolute best to protect the motoring public.